Alright, in this tutorial, which is the second of two tutorials that make up the teaching of protein synthesis, we'll look at translation. This is the second part of protein synthesis. Let's just start again very quickly by looking at what's happening in the overall cell, just to remind you of what's going on. So if we have our cell, we've got our nucleus, and if you've looked at the other tutorial, you'll know that it's in the nucleus that transcription has occurred to produce a piece of messenger RNA. I'll just do that again. So a piece of messenger RNA. So this is transcription, which we've just gone through. This piece of messenger RNA will move out into the cytosol, and it's going to attach itself to a ribosome. Remember, the ribosomes are much, much smaller than I'm drawing them here. So the messenger RNA will attach itself to a ribosome, and then this step here, which is translation, we'll see amino acids brought up from in the cytosol to the ribosome and constructed into a particular sequence based on the code along the messenger RNA, and it's this sequence which becomes the protein. Now, we've just had a look at great length of what happens in transcription in the nucleus. Now let's have a close look at what happens in translation. Now again, complex looking diagram, but you'll be well and truly used to this by now and realise that you shouldn't be fazed by it, and perhaps again pause the tutorial and have a very good look at exactly what's going on, and you'll be surprised at just how much you can recognise. So I'll talk you through the process, and one thing I would recommend here very strongly is to hop onto YouTube and type in protein synthesis and have a look at some of the magnificent animations that are shown on YouTube, and you'll get a look at how this all happens in motion. It's very hard to show you this in a still picture. But I'll talk you through the steps, but have a good look at a number of different animations on the web, and you'll get a very good sense of what's going on in protein synthesis. Alright, so what's going on here? Okay, so the messenger RNA, remember, after post-transcriptional modification, so the final piece of messenger RNA that carries only the coding sequences, will move out into the cytosol and attach itself to a ribosome, or in some cases, multiple ribosomes. Well, let's just have a look at the simple situation here of it attaching to a single ribosome. These ribosomes will be located along the membranes of the endoplasmic reticulum in many cases. So here we see our piece of messenger RNA. Along the messenger RNA there will be a series of bases, a base sequence. And you remember that the base sequence is divided up into triplet codons. So the sequence is read 3 bases at a time. And a series of 3 bases corresponds to a particular amino acid. And you'll remember that from looking at the genetic code earlier in the year, or from the other tutorial on the genetic code. So, what goes on? As the messenger RNA feeds through the ribosome, or the ribosome effectively moves along the messenger RNA, the amino acids have to be brought up and placed into the right sequence. So how does this happen? Well, we have another kind of RNA, that is transfer RNA, out in the cytosol, and you'll see that this RNA, as we've seen earlier in the year, has a rather peculiar shape, but it's still just a single-stranded nucleic acid, but it's folded into a particularly unusual shape. Looks a bit like a cross with loops on the end of it. It has 2 key parts along its length. It has one part which is capable of binding to an amino acid. In this example I'm circling, this one's picking up the amino acid glycine, GLY. So at one end of the tRNA, glycine or amino acid is picked up. At a loop on the other end of the tRNA, in here, there are 3 particular bases in the sequence that are referred to as the anticodon. An anticodon is a series of 3 bases that will be complementary to a codon. In other words, they'll be capable of temporarily connecting to a codon on the messenger RNA. So let's see how this is working in this diagram. Let's have a look at these tRNA molecules here. So here's a tRNA molecule, that is picked up the amino acid valine from the cytosol and brought it up to the ribosome. And here we have, on this end of the tRNA, the anticodon CAC, which is capable of only binding to its complementary bases, which would be GUG on the messenger RNA. So where we see this triplet codon on the messenger RNA, GUG, only the tRNA with CAC can bind to it. And it binds to it using hydrogen bonds only temporarily. So this binding here is only temporary. While it's bound temporarily to the codon, the amino acid valine is linked chemically via a peptide bond to the amino acids that have gone before it. So it will be bound up via a peptide bond to glutamine, as shown here. In the next codon that's being read in this particular example along the messenger RNA, AAA, only the tRNA molecule with the anticodon UUU will be capable of binding to it, and this tRNA will pick up the amino acid lysine, and lysine is the amino acid that corresponds to AAA in the genetic code. Lysine then will be bound by a peptide bond to valine and join the sequence of amino acids. As this happens, the tRNA molecules that link their amino acids into the sequence then drop the amino acid, and they themselves are then free to go and pick up another amino acid of that type. So they're like little taxi molecules. So valine will be dropped off, and this molecule will leave and go and pick up more valine. This molecule will drop off lysine, and it will go and then pick up more lysine. And then we have the next one coming up. So the next triplet code UGC will bind to ACG, and cysteine will be inserted into the sequence. Then this one will come up and insert its amino acid into the sequence, and so on until a stop codon is reached on the messenger RNA, and the process will stop. The whole process begins at the other end with the start codon, AUG, which corresponds to the first amino acid in any sequence, which is methionine. Alright, so in this way, tRNA brings up as many amino acids as is encoded in the messenger RNA, and the amino acids, of course, will be bound together into a primary structured protein. And you've learnt a lot about that earlier in the course in Unit 3. Let's have a look at another diagram just to reinforce what's going on here. So, very similar thing in this diagram. And it's worth just maybe again pausing it and having a good look through it. I'm just going to expand out one part of this diagram for a moment, and then I'll bring the next bit up in a moment. So again, have a good look at what's going on. So you have your messenger RNA transcript coming out. The ribosome will move along the piece of messenger RNA. You have your tRNA molecules bringing up specific amino acids, and only the tRNA with a corresponding anticodon to the codon will be able to link its amino acid into the sequence. So again, when you move down to this step here, you'll see what we've just seen in the other diagram. The used tRNA, after it's dropped off its amino acid, will move away. Other tRNAs will move up into the sequence, and eventually you have your primary structure of a protein built together, joined by peptide bonds. I've just moved up the diagram for a minute. What we can see here is just a slight variation on this, just to have something to be aware of. In some cases it says that several ribosomes may move along messenger RNA at one time. This will speed up the process. This structure, that is messenger RNA, ribosomes, plus the growing protein chains, is called a polysome. Ultimately, the polypeptide chains will join together to make one long primary protein structure. That structure that one long primary protein structure, as you know, will then fold into its secondary structures, the beta pleated sheets and alpha coils and so on, and that of course will ultimately, as you know, fold into its highly complex folded tertiary shape. And if you've got a number of different peptides, it's possible you might even join them together to get a quaternary structured protein. All right, and this is the endpoint of translation.